whatever image representation we have seen, that was all in spatial filtering, a spatial domain. Now we are going to see how do we modify those spatial domain values to a frequency domain. So Fourier transform is basically the process of converting this image from spatial domain, that is the pixel values, to the frequency domain. Now what is this frequencies basically? Now, frequencies as in how fast these pixel values are changing. Let's say if I have 0, 255, then 0, then 255, then 0, then it's a high frequency image. But if I have 25, 27, 29, 25, 27, 23, 24, then this is a low frequency image. Then it is a low frequency image. So now why is Fourier transform being used? So Fourier transform is being used so that uh, all these image processing tasks will become easier, helps to filter the image, noise removal, image enhancement, edge detection. All these can be done with the help of Fourier transform. So this is an example of low frequency, and this is an example of a high frequency image, 0 to 55, 0 to 55. This is what we want to capture. So this is the formula for Fourier transform, where it captures the neighboring pixels values and results. So output of the Fourier transform, it will show how much of each frequency exists and where those frequencies are. Like is if there we have so this is basically the Fourier transform for this particular image. So it indicates that there is some lesser brighter regions, and here all these high frequencies are being put in the side regions, in the outer regions. So this particular image has a lot of edges, as you can see, and because there are a lot of edges, there are a lot of transitions from 0 to 255. So it's a high frequency image. A high frequency image will have more of black outer regions and lesser of the center white bright region. So brighter regions are the frequencies with higher energy. Those will be more dominant in the image. Darker regions means frequencies with lower energy. So outer regions, high frequencies, with that means the image has more of edges, textures and noise. But if you have something like, let's say, the image of a sky, it only makes a transition from light blue to dark blue. So it indicates smooth areas. So for image filtering, we make use of Fourier transform. There are three common filters like low pass filters. Now low pass filters means it will allow low frequencies to pass. It will not allow high frequencies, or I might also call it like it does not allow uh, edges to pass. So here it will help to blur the image. It will help to smoothen the image. The reverse is high pass filter. It will block all low frequencies and it will keep high frequencies. It is used for edge detection. The band pass filters keeps only medium frequencies. It removes low and high frequencies. It's the middle, keeping only medium frequencies. This is one example, and as you can see, this has blurred out the image. This has created more edges. This has created more edges and textures in the image, and this is a band pass filter image. Now we are going to see what is image filtering on the basis of this. Image filtering basically modifies the pixel values to improve image quality, and it is used for noise removal, smoothing, edge enhancement and feature extraction. So here filters can be linear or non-linear filters. The linear filters, they perform linear mathematical operations. So output pixel will be nothing but it will be a weighted combination of neighboring pixels, and it's used for image smoothing and enhancement. So there will be an input image, a filter kernel will be there, and then I will get the output image, something like I'll show you. So this is the process. So like there will be a convolution kernel that's being passed, and on that convolutional kernel I will get the final value. Then this, it will be slightly moved ahead, and then the kernel will be applied, and finally to get another value. See here I am doing -1 into 5 plus 2 into 0 plus 6 into 1. This process is being applied here. With the help of linear filters, it helps, that is whatever is the sum of inputs, that will give me the sum of outputs as well. Input, if I increase the input, it will increase the output also. And here this is based on convolution. It will use kernels or masks. And here it makes use of easy mathematical analysis. Now we have three kinds of linear filters: mean filter, Gaussian filter, and Sobel filter. So the first one is the mean filter. It replaces pixel with neighborhood values. So like for example, here as you can see, we have 50. So it will consider a 3 by 3 neighborhood around a pixel, and the value that I'm getting is 50. So right now here for this particular thing, 50 remains to be 50. But if I take 20, here the value might change. The Gaussian filter. Now Gaussian filter means it will give more importance to nearby pixels. So here what I'm getting, this is my kernel. Sum of the kernel is 16. This is my image window. So I have to multiply it everywhere, and then after that, once I multiply, I'll add it up and then divide it by the kernel sum. So 800 I got as the sum divided by sum of the kernel. Kernel is this. So 800 by 16 I got 50. Sobel filter. Now Sobel filter, it's used for edge detection. Again there is a kernel. This is usually the same kernel every time because it's used to detect edges. And here I again calculate the values here, multiply, add it up, and then after that what I get is uh, 80. That is, the gradient value indicates edge strength. So there are certain limitations of linear filters. They might blur image details. They will not show edge preservation. Uh, but they will help to reduce the noise and the edges will become less sharp. Now the nonlinear filters, they help to perform nonlinear operations. Here the output might be totally different from the input. They help in adaptive processing, and they help to preserve edges also. And these are also used for complex noise removal. So we have three. It removes salt and pepper noise effectively, helps to preserve edges. It responds to local image characteristics, like whatever is locally information available in the image, that is being preserved, and it makes use of advanced mathematical operations. So we have three kinds of nonlinear filters. One is the median filter, morphological filters, and the adaptive filters. First one is the median filter. Now the median filter, center pixel, as you can see 255, is noise because everything around it is of different values. So what I will do is I'll arrange all these values in different order. Now the middle value that I'm getting is 60, so this 255 will be replaced by this 60. Mean is affected by outliers, but median is not, and hence median is the better solution when to remove salt and pepper noise. Then there is morphological filters. Now morphological filters, as you can see here, single white pixel is noise. So now all the neighbors are not 1, and so it will replace the result with 0. And the last one is adaptive filter. Now in adaptive filter, first of all, it will take the average of the neighboring pixels. And then there will be a threshold that will be set. Let's say if the threshold is 93.7 and the center pixel is 97. So 97 is more than 93.7, and so it will change to 255. Rather, if I would have got it 90, the 90 is less than 93.7, so it would have changed to 0. Is it something like threshold is being applied after a particular value? So these are the different filters: mean, Gaussian, Sobel. These are the linear filters. Median, morphological, and adaptive. These are the nonlinear filters. These replace with average of the neighbors. They replace with weighted average. They compute gradient using kernel multiplication. It's basically to detect edges. Then median, replace with the median of the neighbors. Morphological, it will modify shape. And last one is adaptive. It will help to apply threshold. So applications of linear filters. Linear filters are used for image smoothing, basic edge detection, blur reduction, and pre-processing. Whereas non-linear filters are used for salt and pepper noise removal, medical image enhancement, object boundary preservation, and adaptive image restoration. So a low pass filter allows low frequency components to pass. It will smoothen out the image. That is, it will try to remove, smoothen out means it will try to remove that harsh edges, those high frequency edges, and bring blurriness, kind of blurriness to the image. Mean filter is a low pass filter. Gaussian is also a low pass filter. Median is a non-linear low pass filter. Sobel filter is a high pass. It helps to detect edges. Morphological is not low pass or high pass, and adaptive thresholding is also not low pass or high pass. I will show one example corresponding to this. I will show one example using, let me show one example for this salt and pepper noise. So here I will call the image as, so this is one good example. So this is the image, and we will see this is the original image, and you can see that this is the mean filter, Gaussian filter, Sobel filter, and this is the median filter, and you can see how the median filter has clearly helped to remove the salt and pepper noise. So this is how these different filters work. Sobel filter is mostly used for edge detection. Like this, we can try these different types of filters for various kinds of images.